Good morning everyone. Today we'll start a new topic of class 12, that is current electricity. Though to tell the truth, this topic is not totally new for you. You have already learned about current electricity in class 10. Okay. So definitely in class 12 we'll learn little more, but the basic things that should remain same. So today's class you can take it as a remembering class where I just make you remember what you have learned in the previous class. And my suggestion is that after today's class, it is your responsibility to go through the books of class 10 and understand the concept of current electricity theory. Okay? So coming to the term current electricity. In previous chapter we have learned about electrostatics, and where we have told in this part we have to learn about the charges where they are static. And in current electricity, here we have to learn where the charges are moving. Okay, so current electricity means in this part we have to learn about the charges which are moving, which are not static. Okay, so as we are talking about moving charges, so when a charge moves, so it needs a medium to move through it, and we know for that we need a conductor. Okay, so definitely it cannot able to move through insulators. So whenever we have learned about electrostatics, so there mostly we deal with insulating material or insulators, but here we have to learn about the conductors. So when the charge is moving through the conductor, okay, then we will get electric current. That we all know, that when the charges move through the conductors, then we will get electric current. Now the question has come, how do you measure the electric current? So it is also very easy, and you have learned from very early classes that the rate of flow of charges through a cross section is known as current. So that is a very common definition, and you have learned it earlier also. So if there is a conductor, we are assuming, and there q amount of charge is passing through it in time t, then we can say that current I equals to q by t. Okay, so for constant charge q, for constant charge q, current I equals to q by t. But assume it is also possible that the amount of charge passing through a conductor, it is not constant. Sometimes it is q, sometimes it is increased, sometimes it is decreased. So if the charge varies through a conductor, then how we can able to find the current? So for that case we will take a help of differentiation. What is it? Now for that case we will not take a time t, we will take a very small interval of time, that is small interval, that is del t. Okay, so how much small it is? We are assuming that is very small, tends to 0. So we can mention, just remember class 11, del t tends to 0. Okay, del q, so in very small time del t, the amount of charge passing through a cross section, that should be del q. So del q by del t, and it is written as dq by dt. That is differentiation of charge with respect to time. By that we can able to find the current I is equals to dq by dt. Okay, so it is for constant charge, and here if the charge varies, then we can able to find the current. So that is only the extra thing we have learned. So in current, the extra thing we have learned, that is here. Okay, I am coming about unit. So we all know that the unit of current, that is I equals to q by t, that is coulomb by second, coulomb second inverse, which is known as ampere, which is denoted by capital A, and which is also a fundamental unit. Okay, the SI units we have taken, the 7 fundamental units, one of the units are this ampere. Okay, and how we can able to define ampere? Definition of current ampere, if I want to define 1 ampere, so let dt equals to 1 second and dq equals to 1 coulomb. Okay, so definitely I equals to then 1 ampere. So if I want to define it, we can say if 1 coulomb of charge is passing through a conductor in 1 second, then the amount of current should be 1 ampere. So that is the definition of 1 ampere current. Next target is to learn the conventional direction of current as well as what type of quantity it is. Okay, so conventional direction and quantity. So definitely you all know, if I have to make a circuit by this way, okay, so this is a cell which creates potential difference, okay, and for that reason a current is passing through from positive to negative. So that is the conventional direction where the current passing from positive to negative. And here we told that it is the direction of current will be the direction of positive charges. Because as we are starting from positive terminal and going to the negative terminal, so the positive charges are moving, then what will be the direction of movement of positive charges? That will be the direction of the current. But we all know that there is no positive charges in a conductor. Which is responsible for taking the current from one portion to another? So that is basically free electrons. What is free electrons? That is several times discussed in the previous class. It is discussed by me sometime. It is discussed by another teachers also. So I think you all know what is free electrons. The electrons in the last orbit of a conductor. Okay, and the free electrons are there for the conductor. So what is the direction of electron or direction of motion of electron? The electron, or rather free electrons, passing from negative to positive terminal. Okay, so free electrons are moving from negative to positive terminal, and we are taking the current is passing from positive to negative terminal. So we can conclude here the direction of current is opposite, current flow is opposite to the flow of electrons. So it's a very simple thing, and you have learned also earlier that electrons, they can able to move in a particular direction whenever you have give it a particular potential difference. But the positive charges, what we are talking about, exactly there is no positive charges. Okay, so when electrons are moving one particular direction, we assume that the positive charges are moving in opposite direction, and that should be the direction of current. Now talking about the quantity, what type of quantity it is? Current is a scalar quantity. it is a scalar quantity. Okay. Now you might be asking, sir, just now we are talking about the direction. If I am talking about 5 ampere current, so there is a magnitude 5 and there is a direction from positive to negative. Then why you are telling that current is a scalar quantity? Current is a scalar quantity because it doesn't follow the vector algebra. So we have learned vector algebra in class 11. If you have forget, then my suggestion is go and learn it again. So as it doesn't follow the vector algebra, that means vector addition, vector subtraction, vector multiplication. So this one, they should have a different rule. I think you have read it. So as they have not followed it, that's why current is taken as a scalar quantity. Right? I think it is clear. Now we'll learn a new thing. That is a new concept for you. That is current density. So first try to understand what it is. Then I'll explain why it is a need to learn this quantity. Okay. What is current density? Current density means current passing per unit surface area is known as current density. Current passing per unit surface area. Okay, what does it mean? Assume it is a conductor. Okay. And the current is passing, del Q amount of charge is passing through this conductor. Right? In this conductor, there is an area of cross section they are passing. So assume this is the area of cross section of the conductor. Okay. And the current is passing this area of cross section. Right? What will be the area of cross section? I am assuming for the small charge del Q, the area of cross section is del S. Right? And it will take a time del T to passing through the surface. So if I want to find out what is the amount of current I, so I equals to del Q by del T. And if del T is very small, that means if we write that limit del T tends to 0, del Q by del T, so it should be dQ by dt. That is our current. Now the current is passing a surface area del S, right? It is passing a surface area del S. So assume the current density then, current density which is denoted by J, okay, small j. So current density is denoted by small I by del S. Small I by del S, that is current per unit area. Current per unit area, that is known as current density. J equals to I by del S. Now, what should be the unit of it? If anyone asks you, what should be the unit of it? So unit will be I, that is ampere, by del S, that is meter square. So ampere meter to the power minus 2. Ampere meter to the power minus 2. Now the question has come, what is the need of it? What is the need of it? Now, whenever we have drawn this diagram, in this diagram it is very clear. So this is the area and the current is passing I by del S. Assume, if I assume the surface area like this way, here we are taking surface area in a very straight way. Assume the surface area is just like this. So the del q is passing like this way, right? So that is the direction of the charge del q. And if I am talking about surface area, it is a vector quantity, so the direction of it is perpendicular to it. So it is the perpendicular on the surface. So there is an angle. How much? We are assuming the angle is theta, and the surface area is del S. So now, if anyone asks you the amount of surface area is just getting a phase along the direction of the charge, means the amount of surface area along the direction of the charge. So we will take this component. What will be this component? It will be del S cos theta. It will be del S cos theta. And here, if I want to find J, so J equals to I by del S cos theta. Why we are taking del S cos theta? Because the direction of the surface, you see here, the direction of the surface is acting along its perpendicular, which is here, but we have to take along this direction, along the direction of the charge. Okay, so if I write it this way, then I equals to J dot del S cos theta. I equals to J into del S cos theta. And here we can mention that I equals to J dot del S. That is the dot product. J dot del S. And by this we understand one thing. What is that? That J is a vector quantity. J is a vector quantity. So initially we have seen that current is a scalar quantity. But later when we find current density, and there we have to see that current is coming by taking a dot product of two vector quantities. So that's why current is a scalar quantity. We know whenever we have to find a quantity which is coming by the product, by the dot product of the two vector quantities, that should be a scalar quantity. Just like if I am talking about work done, so W equals to F dot S. So F is a vector quantity, S is a vector quantity, but W is a scalar quantity. Here also J is a vector quantity, del S is a vector quantity, but it is a scalar quantity. And if we assume that this del S is very small, and if I want to find the total current from here, so total current will be total current I, it will be equal to integration of J dot ds. J dot ds. If ds is small, so we can able to find the current by taking an integration of current density with the surface area. So current density means here this current density is introduced to vectorize the current electricity, because initially we have seen current, it is a scalar quantity. So how we can able to vectorize it? So that's why we have taken another quantity, that is current density. Okay, I think it is clear. Next our target is to learn potential and potential difference. So it is not new to you, you have already learned that to take the charges from one point to another point, we need to give a potential difference. Otherwise, the charges cannot able to flow. So I have told earlier also. So if anyone asks you that until you have not given potential difference, the free electrons are not flowing, they are static. No, the free electrons are flowing, but the free electrons are moving in haphazard direction. The direction is not particular, but to get a current, we need a particular direction of flow of electrons. So that particular direction is given by potential difference. Now the question has come, how the potential difference has come to a conductor and how the potential has come to a conductor. If I have told you that in electrostatics we have already learned that how a charge acquire a potential. I think you have learned now that if I am taking a positive charge in one point and I have taken another positive charge from infinity to that point, how much work we have to do, right? So to take a unit positive charge from infinite to a point in an electric field, what work has to be done, that is known as potential. So definitely by this way, in a conductor, the potential is created. As you have connected two terminals of a cell, there this cell will create a potential difference. So we have already learned, I am not going in very much details of potential because we have learned it earlier. So the work done, W, is proportional to the charge, the amount of charge you have taken, and W equals to V into Q, where V is a constant and this V equals to W by Q, and it is known as potential. And as Q equals to 1, then V equals to W. So from here only we can define, to take a unit positive charge from infinite distance to a point on an electric field, what work has to be done, that is known as potential. Okay. And what is the unit of it? So that is also very much clear, that joule per coulomb, that is joule coulomb inverse, which is volt. I think I have given a question of test for electric potential, and there we have marked which physical quantity is having a unit joule per coulomb, and that is electric potential, that you all know. Now the question has come, what type of quantity it is. As it is dealing with work done and charge, both are scalar quantity, so it is also a scalar quantity. It shouldn't have any sort of direction. So as a conductor will get potential in two different points, in one point it is getting higher potential, in another point it is getting lower potential. In a conductor, assume a point A and here is a point B. Here the potential is VA, here the potential is VB. So what is the difference between the potential? That is VA minus VB. Okay, that is equals to V. That is known as potential difference. And as the potential difference is created, then a charge Q is passing from higher to lower potential. That is very common, we all know that. That's why I am just moving a little faster. So to take a charge from one potential to another potential, what work you have to done, that work done per unit charge is known as the potential difference. So here we can write that V equals to W by Q, and here V means VA minus VB, that is equals to W by Q. So it is clear that except potential difference, we cannot able to pass a charge from one point to another point. If I am talking about the direction of electrons, definitely the electrons are coming from negative or lower potential to higher potential, and from higher to lower current is passing, that is the positive charges. And what is the lower potential we are talking about? Mainly we can say that there it is a storage of negative charges, and in higher potential we can say that there is a storage of positive charges, and that's why this circle is continuous, and that's why we can able to get the current flow through a conductor. So cause of current flow is potential difference, and we all know that this cause is first explained by the great scientist Ohm, and you all know that in class 10, the very important part of your current electricity portion is your Ohm's law. And here also there is a glimpse of Ohm's law, but we will not go in details. So Ohm's law, what we know, that potential difference, the current passing through a conductor is directly proportional to the potential difference. And here we are taking a constant to make it equal, and this constant has a name that is known as resistance. Okay, and why this resistance have come to a conductor, that we will discuss. But what is resistance? So resistance is a physical quantity which produces a opposition force to the flow of charges. So resistance is a property of a conductor, you can say that, by which it cannot allow current to pass through it. Okay, so definitely if you give same potential difference also for different conductors, there the amount of current will be different, because for different conductor the value of resistance will be different. So as the value of resistance is different, so the amount of current passing through the conductors is also different. Units: R equals to V by I, okay, and volt by ampere, and it is known as ohm, and it is denoted as this. So it is very well known to you. Okay, so I'm not giving much time here, I'm just making you remember what we have learned in class 10. Now if anyone asks you what is the cause of resistance in a conductor, cause of resistance in a conductor, we have already learned it, that to flow the charges from one point to another point, which thing is responsible? The responsible thing is free electrons. We all know that. Free electrons means, if I am just draw atomic structure like this, so assume in first there are 2 electrons, then it is 8, and assume here it's 2. So these last 2 electrons are known as free electrons. Okay, but as the free electrons, we can say that it can move any direction, but this portion, this is a stable part, this is known as inert part of atoms. As the electron comes outside from the last orbit, then this inert part of atoms is converted to a positive ion. So when the free electrons are moving through the conductor, these positive ions, they are already on their path of free electrons. So as the free electron moves, this positive ion comes in front of them. So definitely there will be a collision. So as there are collisions between the free electrons and the positive ions, then the motion of the free electrons are hampered. So as the motion of the free electrons are hampered, so the amount of current is decreased, and that one is known as resistance. So depending on the size of the positive ions and depending on the number of free electrons, the resistance of a conductor changes. That is the internal property of a conductor. I think it is clear. Okay. Now we have to come to know the next thing, the factors on which resistance depends. That also is very much, you are very much familiar with it. Factors on which resistance depends. And by the way, this resistance is also a scalar quantity. It shouldn't have any sort of direction, so that's why it is a scalar quantity also. Factor on which resistance depends. We all know resistance depends on the length of the conductor. Why? I will not give any explanation. You have already got it in class 10. Read the book. If you have not understood, then we will explain. R is directly proportional to L when A is constant, where A is the cross section, right? R is proportional to 1 by A, or R is inversely proportional to A when L is constant. So if you increase the length, the resistance will increase. If you increase the cross sections, the resistance will decrease. If you write it together, that is R is proportional to L by A when L and A both are changed. Now we need a constant. Now here in class 12 you have to learn about it. Why there is a need of a constant and what is the physical significance of the constant? See, if I am assume 3 conductors of same length and same cross section. Okay, so assume it is copper, it is zinc and it is aluminium. 3 conductors. Okay, both are having same length, that is L, and cross section A. If you given a potential difference to it, is it same current passing through the conductors? Same current will passing through the conductors? The answer will be no. Why? Because just now we have discussed that when the resistance will appear, the main thing is the internal property of a conductor where the positive ions are collided with the free electrons. So the number of positive ions or the structure of positive ions and number of free electrons is not same in these 3 elements. So the resistance will be different. So some quantity is needed which explains the internal property of the conductor, and that is taken by one quantity, that is resistivity. Okay, and what is the unit of it? Rho equals to RA by L. So R means ohm, A means meter square, and it is meter, so it is ohm meter. Up to this you have learned in previous class. So now I will introduce little more thing. This thing is known as resistivity, and along with it we have to learn one thing, that is conductivity. What is conductivity? Conductivity is denoted by sigma, and sigma is the reciprocal of resistivity. If I have taken the reciprocal of resistivity, it is known as sigma. What is the unit of it? That is 1 by ohm meter. So we can mention it is ohm inverse meter inverse. Okay. If I am talking about, as we have learned about resistance R, we know resistance is equals to R and whose unit is ohm. One another quantity we can introduce, that is conductance, which is G and which is the reciprocal of resistance, that is 1 by R. It is 1 by ohm and it is known as ohm inverse. Okay, so there is another name also. The another name is known as mho. Why it is mho? You see, whenever we have written ohm, that is denoted by this one. But as we have denoted ohm inverse, so it is the reciprocal. Mho, M-H-O. Okay. Another unit also it is given, that is known as Siemens. Okay. But it is not needed to learn. So these are the resistance, resistivity, the things we have discussed here. Now along with it, one important thing comes to our mind that we should discuss. What is it? That thing is, we have learned about Ohm's law, right? We have learned about Ohm's law. But only to learn Ohm's law is not enough here. Here you have to learn about the vector form of Ohm's law. Vector form of Ohm's law. What is the vector form of Ohm's law? As we have seen earlier that V equals to IR, that is the Ohm's law. And here you see all the quantities we have written, all the quantities are scalar. V, it is scalar, I, R, everything is scalar. So if I want to get a vector form of it, then what we need to do? Let's see. Now vector form of Ohm's law we can derive later also in different method. Okay, that is known as drift velocity. But here we have to mention it in a general process. So now you have to ask, sir, if it is coming in exam, which one we have to follow? So if it is mentioned that you have to find the vector form of Ohm's law by the help of drift velocity, that we will discuss later. And if it is write down only to find out vector form of Ohm's law, you can do by it any process. So let's see. If I am talking about potential difference V, that can be written as E into L. So now you can ask me, sir, how you can write this thing? So we can write it by the help of electrostatics. Remember that V we have got, that is E dot L. So definitely we get vector and V equals to E dot L. We can write it. Okay. Now coming, why it is written? So see the previous chapters, you will understand. Now we're coming again. V equals to I into R. We have already mentioned. R equals to rho L by A. So can I write V equals to I into rho L by A? Clear? Now I by A, current by area. So current by area means what? That is current density, J rho L. So J equals to I by A. What is current density? Just now we have discussed. Okay. So V equals to E dot L, and here if I am taking rho in this direction, so J dot L, V equals to. So let's combine it. So if it is equation 1 and if it is equation 2, so 1 equals to 2, both are representing V. So E dot L, that is equals to rho into J dot L. So L will be cancelled out. E equals to rho into J. That is also one form of Ohm's law. And here you see the vector form has come. E and J both have vector. Now we know rho equals to 1 by sigma. So if I write here E equals to 1 by sigma into J, or J equals to sigma into E. So that is also the vector form of Ohm's law. It is also the vector form of Ohm's law. Effect of temperature on resistance. Okay. So how the resistance changes with temperature? Now the answer is clear. You have already learned that as the temperature increases, the resistance will increase. Why? What is the reason behind it? Now as the temperature increases, then the motion of the free electrons as well as the motion of the positive ions are very much faster. And that's why the effect of collision or the probability of collision, it will increase. And that's why the resistance increases. Now our target is to learn how the resistance increases and how much the resistance increases. Let at temperature T0, okay, means assume it is initial temperature, resistivity is equals to rho 0. Now you can ask, sir, why we are taking resistivity? So definitely the internal movements of the positive ions and the electrons, it is denoted by resistivity. That is the internal property, it is denoted by resistivity. So as the collisions increase, that means definitely the resistivity will be changed with the temperature. So at temperature T0, the resistivity will be rho 0. At temperature T, okay, the resistivity equals to rho. Okay. Now, how much the resistivity change? So change of resistivity, that should be rho minus rho 0. It is told that this change of resistivity, it is directly proportional to the temperature change. Temperature change means how much temperature you have changed. Now, final temperature is T and initial temperature is T0. So T minus T0 or T minus T0. Again, rho minus rho 0, it is directly proportional to the initial resistivity. So initial resistivity is how much? Rho 0. This is the law. Just like whenever you have learned about the expansion of length, expansion of volume, remember in class 11, same thing it is here. Okay. So if I write it together, rho minus rho 0 is directly proportional to rho 0 into T minus T0. So it is clear the probability of collision, it is different for different elements. So for that reason we have to take a constant quantity here, and that constant quantity is alpha. Rho 0, sorry, T minus T0. What is alpha here? Definitely alpha is a constant and whose value is which known as temperature coefficient of resistivity. Temperature coefficient of resistivity. Now, how we can able to find the value of alpha? So alpha, it is equals to rho minus rho 0 by rho 0 into T minus T0. That is alpha. So here we can mention it, or we can it's rho 0. So if rho 0 equals to 1 and T minus T0 equals to 1, then alpha is equals to rho minus rho 0. Exactly same with class 11, you see. Exactly same. So that means we can define, if I increase temperature by unit of a unit resistivity, then the change in resistivity will be the temperature coefficient of resistivity. Right? Okay. So unit temperature increase of unit resistivity, then the change in resistivity will be the value of alpha. If I am talking about the unit, so unit will be rho minus rho 0, that is the unit of resistivity. Rho, it is also the unit of resistivity, cancel out. It will be 1 by temperature difference, that means Kelvin inverse in SI. In SI, the unit of alpha will be Kelvin inverse, just like the coefficient of expansion of length, coefficient of expansion of area, coefficient of expansion of volume, alpha, beta, gamma, we have learned in class 11. So if I write it in this form, that is, I'm just writing from here, rho minus rho 0, that is alpha rho 0 into T minus T0. If I am taking rho 0 there, so rho equals to rho 0 plus alpha rho 0 T minus T0. and rho equals to, if I've taken common, 1 plus alpha T minus T0. So if T minus T0 you have given del T, if T minus T0 equals to del T, then we can mention rho equals to rho 0 into 1 plus alpha del T. So that is the change of resistivity with temperature. If you increase del T temperature, then your resistivity will be changed by rho by this way. If you multiply both sides L by A, multiplying L by A in both sides, if I multiply it, so what we will get? Now we will get rho L by A equals to rho 0 L by A into 1 plus alpha del T. It is as it is. Rho L by A means R, rho 0 L by A means R0 1 plus alpha del T. So if I know the change in resistivity with the temperature, I can able to find the resistance also. We can able to find the resistance also by this formula. So where alpha is temperature coefficient of resistance. Now how this temperature coefficient changes? Okay, how the resistivity, as the temperature coefficient is changes, the resistivity will be changed. So how resistivity is changed with temperature for different conductors, if we see, okay, then we can able to understand what thing we will use to measure the resistance or to create or to produce the resistance in a circuit. Okay, let's see it. Assume I am taking a graph. Along x-axis I am taking temperature. Along y-axis I am taking resistivity. Now if I am taking copper as a conductor, so if I increase the temperature, the resistivity of the copper varies this way. What it signifies? It signifies that whenever you increase temperature, initially its resistivity increases linearly, but suddenly by changing a very less amount of temperature, the resistivity goes to a peak. So we can say the change in resistivity with temperature for a copper conductor, it is not linear. So we cannot use as copper for a proper resistive material in a circuit, because you know in a circuit we use resistances several times, so we cannot able to use copper here. First of all, the resistivity of copper is very low, and that's why the amount of current flow is more. Along with the temperature dependence with the resistivity for copper, it is not linear. Rather, if I am taking an alloy, same thing here, temperature and here resistivity. If I am taking an alloy that is nichrome, you all know that it is an alloy of chromium and nickel. You see, its resistivity changes with temperature. It's almost linear. It is in a straight path. So as you increase temperature, you are having a law that the resistivity also increased in a linear way. So it is more often used as a resistance rather than copper. Not only nichrome, if you take manganese, if you take constantine, all these are alloy. So these alloys are very often used as to make resistances in a conductor, because they have show linear progression with the temperature. Okay, but in copper we have not seen. And instead of taking the conductors, if I am taking a semiconductor, though you will learn semiconductor little later, but what will happen with the semiconductor or the resistivity of semiconductor? You see, if you increase temperature for a semiconductor, surprisingly the resistance will decrease instead of increase. What we have seen in conductor, for the case of semiconductor it is totally different. For semiconductor, that will be the relation, means whenever your temperature is here, means low, the resistivity is high. As you increase the temperature, the resistivity is decreased. A very interesting thing. The resistivity decreases. Why? Whenever you have to learn semiconductor, then I will explain. One thing we can mention here, that using this property of semiconductor, we have made one instrument that is known as thermistor. What is thermistor? So thermistor is nothing but a semiconducting device, is just connected in a circuit. Okay, it's a semiconductor material is connected in a circuit. What is happened with it? Now as the temperature is increased, we have seen the resistance of the semiconductor decreases. What we have done, you know, we have just connected with a cell, clear, and then we have put inside in a water bath or any of the liquid material we want to find out the temperature of it. So this setup, we just keep it here like this way, and then there is a connection and is connected with the same. So as we have given heat to the bath, to the water bath, the temperature of the water is increased. So as the temperature is increased, definitely the resistivity of the semiconductor will decrease. And if I connect here one ammeter, so ammeter you all know, it is measure the current, we will see the amount of current is increased. So based on the amount of current, we can able to find the temperature of the water. So that is the use of thermistor, right? So these are the resistances, and these manganese, constantan and nichrome, this materials or these alloys are mainly used to make wear resistances. You have to do practical in your school, and then you have to see that their maximum case manganese is used. Okay, for today it is enough. Read up to this, and then we learn in the next part of the video. Thank you.